Hello everyone, welcome to the session on operating systems. In this course, we will learn how the OS manages the CPU, memory processors, and devices, and how it acts as a bridge between users and hardware. Let's begin our journey into the core of computer systems. Introduction to operating systems. An operating system OS is a system software that acts as an interface between the user, applications, and computer hardware. It manages hardware resources efficiently and provides services for program execution. The primary objectives of an OS are convenience, efficiency, and ability to evolve. A typical operating system performs essential functions such as process management, memory management, file management, I/O management, and protection. Modern operating systems are designed to support multitasking, multi-user environment, and high performance. Operating systems can be classified into batch systems, time-sharing systems, real-time shared systems, distributed systems, and embedded systems. Over time, OS design has evolved from simple batch processing systems to complex, interactive systems like Linux and Windows. Operating system services. Operating systems provide a set of services to both users and programs. These services include program execution, I/O operations, file system manipulation, communication, and error detection. For efficient system operation, the OS provides resource allocation, accounting, and protection and security services. These services ensures that system resources such as CPU, memory, and I/O devices are shared fairly and securely among multiple processors. Overview of operating systems and kernels. The kernel is a core component of an operating system that runs in privileged mode and has complete control over system resources. It manages CPU scheduling, memory allocation, and hardware interaction. There are different kernel architectures such as monolithic kernels, microkernels, and hybrid kernels. Linux uses a monolithic kernel with modular design, allowing dynamic loading of kernel modules. Linux kernel versus classic Unix kernel. The classic Unix kernel was designed for simplicity and stability, whereas the Linux kernel is highly modular, scalable, and supports a wide range of hardware platforms. Linux provides better support for multi-threading, multiprocessing, SMP, loadable modules, and advanced scheduling. While Unix systems are often proprietary, Linux is open source, allowing continuous improvement and community driven development. Process concept. A process is a program in execution. It consists of program code, current activity, CPU register, stack, heap, and data section. Each process has a unique process ID (PID) and is represented in the OS by a process control block (PCB). The PCB stores important information such as process state, program counter, registers, scheduling information, and memory management details. Processes can be in different states such as new, ready, running, waiting, or blocked, and terminated. The operating system manages transitions between these states. Process states and data structures. Process management relies heavily on data structures like the PCB, ready queues, and waiting queues. The OS maintains these structures to track all active processes. State transitions occur due to events such as I/O requests, interrupts, or scheduler decisions. Efficient management of these states is crucial for system performance. Process Control Block (PCB) is a data structure maintained by the operating system to store information about a process. It contains details such as process ID, process state, program counter, CPU registers, and scheduling information. The PCB helps the OS manage processes and is essential during context switching to save and restore process states efficiently. Process creation. Processes are created using system calls such as forkoff, xoff, and waitoff in Unix and Linux systems. The fork of system calls creates a new child process by duplicating the parent process. The scope call replaces the processor's memory space with a new program. Process creation involves allocating resources, assigning PID, and initializing the PCB. Process sharing among processes. Processes may share resources such as memory, files, and I/O devices. Sharing improves performance but introduces challenges like race conditions. The OS provides synchronization mechanisms to ensure safe sharing. Inter-process communication (IPC) mechanisms such as pipes, shared memory, message queues, and signals are used to enable controlled data exchange. User mode and kernel mode. Operating system operates in two modes: user mode and kernel mode. User applications run in user mode with restricted access to hardware, while the kernel runs in kernel mode with full privileges. Transitions between these two modes occur via system calls, interrupts, and exceptions, ensuring system protection and stability. Context switching. A context switch occurs when the CPU switches from executing one process to another. During a context switch, the OS saves the states of a currently running process in its PCB and restores the state of the next process. Although necessary for multitasking, context switching introduces overhead and must be minimized for better performance. Threads and concurrency. A thread is the smallest unit of CPU execution within a process. Threads share the same address, space, and resources of a process but have their own registers and stack. Multithreading improves application responsiveness and resource utilization. Concurrency allows multiple threads or processes to make progress simultaneously, which is essential for modern multi-core systems. Benefits of multithreading. Multithreading offers benefits such as responsiveness, resource sharing, economy, and scalability. It allows a program to continue execution even one thread is blocked and improves CPU utilization by parallel execution. Multithreading models. There are three main multithreading models: many to one, multiple user threads mapped to one kernel thread; one to one, each user thread mapped to a kernel thread; many to many, multiple user threads multiplexed over multiple kernel threads. Linux primarily uses the one-to-one model, providing better concurrency and performance. Linux implementation of threads. Linux implements threads using lightweight processes (LWP). Threads are treated as processes that share resources. The clone of system call is used to create threads by sharing selected resources such as memory, file descriptors, and signal handlers. Process scheduling. Process scheduling determines which process gets CPU time. The scheduler aims to maximize CPU utilization, throughput, and fairness by minimizing waiting and response time. Scheduling decisions are based on algorithms and process priorities. Basic scheduling algorithms. Common scheduling algorithms include first come, first serve (FCFS), shortest job first (SJF), priority scheduling, round robin (RR). Each algorithm has advantages and disadvantages depending on system requirements. Multi-level feedback queue (MLFQ). The multi-level feedback queue scheduler uses multiple queues with different priorities. Processes can move between queues based on their CPU usage and behavior. This approach allows the system to adapt dynamically and provides a balance between responsiveness and fairness. Linux Completely Fair Scheduler (CFS). The Completely Fair Scheduler (CFS) is used in Linux to ensure fair CPU allocation. It models scheduling as an ideal multitasking process and uses virtual runtime (vRuntime) to track how much CPU time each process has received. Processes with the least vRuntime are scheduled first, ensuring fairness. Thank you for attending this session on operating systems. I hope the concepts helped you understand how modern systems work internally. Keep learning and exploring core computer science concepts. All the best.